Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over a couple of examples of how to calculate reaction rates or problems related to figuring out rates of change of different products or reactants or the rate of a reaction. So in this first problem, it is giving us an equation. So you have hydrogen peroxide aqueous plus iodine ion aqueous plus hydrogen ion aqueous, and then this is going to give you the product of I3 ion and two water, or 2 moles of water, 2 molecules of water. So here's our reaction. And in addition to that reaction, they say that in the first 10 seconds of this reaction, the concentration of iodine ion goes from 1.00 molar to 0.868 molar. So in this time period, you get this change in the concentration of iodine. So two questions are two parts to this problem. So the first question is, what is the average rate? So what is the average rate of the reaction? Okay, and then the second one is, what is the rate of change of the hydrogen plus concentration? So let's do with the first one. So both of these are going to require the average rate of change. So if the average rate of change, there's that equation or that relationship that the rate of the reaction, right, is equal to, and it's you have to factor in the fact that the coefficients, different reactants are changing at different rates because of the coefficients. So in order to keep the reaction rate of the reaction rate the same, regardless of what product or reactant you're looking at, then you need to multiply by the reciprocal of that coefficient, or basically you're dividing by the coefficient. So we're looking at the iodine ion concentration. So here we have a 3 coefficient. And since we're talking about the reactant, so this is a reactant, so this is going to decrease over time, right? So that's going to give us a negative rate. So here, if we look at this, and so if we're looking at the reactant, that's going to decrease over time. So that's going to have a negative rate. Remember the slope. The slope is negative because you're decreasing over time. And so here you're going to have 1 over 3. And then you're going to multiply by your rise over run. So it's going to be the change in your concentration, final minus initial. The final was 0.868 molar. That was the final concentration, minus the initial, which was 1.000 molar. Okay. And so the time is 10 seconds. So that's the time that we're looking at. So the time range is 10 seconds. And so if we calculate this out, then we'll get the rate of the reaction. And so if we calculate that out, I have to find my calculator. Okay, so if we calculate this out, then we get, so it'd be 0.868 minus 1 divided by 10 equals, divided by 3 equals, and we get positive 4.40 times 10 to the negative 3 molar per second. So this is the rate of the reaction. Okay, so that's part A. So we got the average rate of the reaction. And so the part B is, what is the change of the H concentration during the same time? So here we got to be careful. They're not asking about the rate of the reaction. They're asking for the rate of change of the hydrogen ion concentration. So we got to set it up the same way. So we know the rate of the reaction, right? So the rate of this reaction is going to be the same, right? If we say if we use, so this is also going to be equal to to this rate of change in the H plus concentration. However, the coefficient is 2, so it's going to be 1 over 2 times, and then we have delta change in the H plus concentration over change in time, right? So, since we know the rate of the reaction, we're looking for the rate of change in H plus ion, which is this right here. This is what we need to find. So the delta H, the change in delta H over time is 1/2 of that is equal to this. So we can look for the change in the H plus. So this is what we want to find. Okay, so this is 10 seconds. This is 1/2, we know this, so we just solve for delta H, the change in hydrogen concentration. And so that's going to be 4.40 times 10 to the negative 3 molar per second, right? Multiplied by 2, because we're multiplying both sides by 2 to get rid of the 1/2. And then this is 10 seconds, so we multiply both sides by 10 seconds. This is going to be equal to the delta H, oops, not the delta H, or the delta H plus concentration, the change in the H plus concentration. So if we calculate that out, that becomes let's see. Oh, I'm sorry. This I forgot the negative here. So there's a negative here because that is also a reactant, and this is going to decrease over time. So we forgot the negative, so bring the negative over here. So the change in delta H is going to be negative 8.80 times 10 to the negative 2. Let me make sure I got that right. Negative 2, oh, my bad. So we don't want to, so I misread the question. So we want this rate of change over the same 10 seconds. So we don't want to multiply by the 10 seconds. So we want, I was right the first time. So we want this whole thing, this is what we're solving here. So then this is going to be a 3, and that's going to be molar. So this is negative. The change is going to be negative 8.80 times 10 to the negative 3 molar is equal to delta H plus over delta T. So this is the rate of change of the hydrogen during the same 10 seconds. So that's the rate of change of hydrogen H plus, and so this is the rate of the reaction here. So this is the rate of the reaction. So in both parts, we used the formula of rate is equal to 1 over the coefficient multiplied by the change in concentration over the change in time. And that's the way you get the average rate of the reaction or the average rate of change of any of your products or reactants. So what about the next problem? Okay, so for the second problem, in the second problem, same equation, but now they want us to ask, in the second problem, we're going to look at and predict what the rate of change of the two products are, right? So here's the rate of change, so delta rate of change of the concentration of H2O2, the hydrogen peroxide over time, and the rate of change of the I3 minus over time during the same 10 seconds in the last problem. So this was the rate of the reaction. So we can, again, take the rate of the reaction and set it equal to the same expression using the coefficients, right? So the rate of the reaction is 4.40 times 10 to the negative third molar per second. That's going to be equal to, for this H2O2, that's going to be equal to 1. Let me double check my equation. So 1. So this is going to be equal to 1 over 1, just to write it out, multiplied by the change in the concentration of H2O2 over delta T. And this is what we want to find. So since it's 1 over 1, that's 1 times this, then this ends up being the rate of change of the delta H of the hydrogen peroxide over time. And you'll notice that this is positive because we're talking about, oh, I'm sorry, this should be negative, my bad. Okay, so we have a negative there because it's a reactant again. So then this should be a negative 4.40 times 10 to the negative 3. So that's the rate of change of the hydrogen peroxide, which is the same as the rate of the reaction. So for I3 minus, same thing, rate of the reaction is going to be 4.40 times 10 to the negative 3 molar per second. And this time, we're looking at I3, it's 1 again, so I3, so it's 1 again. So this is a product, so it's positive 1 over 1, and again, it's going to be delta concentration, change of concentration of I3 minus over delta T. And again, this is positive, 1 divided by 1 is 1, so we have the positive 4.40 times 10 to the 3 molar per second. So since these are 1 to 1, you're losing hydrogen peroxide at the same rate as you're gaining your I3 minus, and that's because they both have coefficients of 1. I hope this was helpful. If you enjoyed this video, please like, subscribe to the video, hit the like button, hit the notification button so you get notified by any other videos I put out. Hit the subscribe button, subscribe to the channel, and also put a comment in the comment section. Let me know what you think and what other questions you might have. Thanks for joining me, and I'll see you next time.